Hello and welcome to the fourth and final video of the FP2 chapter, Maclaurin and Taylor series. On the screen, a review of all of the different formulas that we've gone through so far that are in the International Formula booklet. Remember, you don't need to memorize these, but you do need to be able to use them. In this video, we're going to use the Maclaurin and Taylor series expansions to solve differential equations. So we've got this here from our Maclaurin series expansion, and if we rewrite that using the dy by dx notation, we get this. Now this hopefully is already starting to look like a differential equation, because we've got these dy by dx's, second orders, third orders, fourth orders, and more. Fortunately, we'll only be focusing on first and second orders, although you can use this method to solve higher order differential equations. So the notes, here we go. The Maclaurin series expansion gives us an alternative way to solve differential equations. First order and second order differential equations that cannot be solved using the methods already seen, because there are some that can't be solved doing what we've done so far. And also higher order differential equations, which we haven't even talked about and don't need to talk about, can be solved to give a series solution. And we use this method. Step 1, we use the known boundary conditions to find the value of this constant and this constant. And when I say find, to be honest, you won't even need to find them. Usually this is the information given in the question. Then you will use those to find, and I do mean find here, you'll end up finding a value for this constant here, the second derivative evaluated at x equals 0. And you do that just by putting in the values you're given to your differential equation in the question. So very quickly, you'll have this value, and this value just from the information given in the question. Then to find the next term, assuming you need a power 3 or higher, you're going to need to have to differentiate your differential equation to find a higher order derivative. So if it's a second order differential equation, you differentiate it to find the third derivative of y with respect to x, and you put in all the values that you've got so far in order to find the value of that, so that you can find this value here. And then you keep going until you get up to the order that you need given in the question. After you've got all of your values, you just put them into this expression here, and that is your series solution. There are quite a lot of questions on this in the textbook, and if you work through the exercise, you'll probably find what I find is that this is quite a repetitive process. Once you've got the idea, it's the same thing every time. The only difference really is how difficult the differentiation gets, and that of course depends on what you start with. So we'll do a couple of examples here. Use the Taylor method to find a series solution in ascending powers of x up to and including the term in x cubed of this second order differential equation. So I know I'm going to have to differentiate this later, because to get x cubed I need to evaluate the third order derivative, and to get that I will have to differentiate this. The boundary conditions that we are given is that x equals 0, y equals 1, and the first derivative is 2 all at the same time. That's important. When x equals 0, y equals 1. These two together are telling us that y0 is 1. This is y0 if this is true when x equals 0. Similarly, the first derivative is 2 when x equals 0. That is this value, the first derivative evaluated at x0. So we've already got these two given to us. We know that y0 is equal to 1, and dy by dx evaluated at x0 is equal to 2. So that's the first step of the method already done. Now we use the differential equation and the values that we've got, put them into here to find out what is this value when x is 0. So we've got the second order derivative, and that is equal to y, but y is 1 when x equals 0, and we're evaluating all of this at x equals 0. So that's a 1 instead of a y, minus sine x, but we know x is 0, Sine of 0 is 0, so that's 1. So this evaluated at x0 is a 1. So far then, we've got a 1 for this, we've got a 2 for this, and we've got a 1 for this. But we need up to x cubed. So we need to know the third derivative evaluated at x0. In order to get that, we need to differentiate this equation here. So if we differentiate the left-hand side, we just get the next derivative up. Differentiate the right-hand side with respect to x gives us dy by dx and a minus cos x. And we do the same thing. To find this evaluated at x0, we just use the values we already know for these at x0. We know dy by dx is a 2 at x0, and of course x is a 0 at x0. So evaluating the third derivative, at x0 is equal to dy by dx, which we know is 2, minus cosine of x, which we know is 0, that's 2 minus 1, that also is a 1. So now I've got all the information I need, I've got all the constants here to put into this equation together with the x's and the factorial numbers here. So my solution, y is equal to y0, which is a 1, plus 2 times x, plus 1 over 2 factorial times x squared, plus 1 over 3 factorial times x cubed, plus dot dot dot. And of course I should simplify that as far as I can. And here is our series solution. To recap, first realize that the boundary conditions are already telling you some of the constants that you need. Then put them into the equation you've got to get the next constant that you need. Then differentiate that equation to get the next constant that you need, and just keep going. If we needed the fourth one, we would differentiate this, and then use all of the constants so far to help us evaluate the fourth derivative, and then the fifth and the sixth, and however many you need. Though hopefully you won't need to go that high. A lot of these questions are very similar, but I've deliberately chosen a second example that is a little bit different to show you something slightly different that could happen. Use the Taylor method to find a series solution of this equation, first order differential equation. Given that y equals 1 when x equals 1, use your solution to find an approximate value for y when x equals 1.1, giving your answers to 3 decimal places. Okay, there are two slightly different things here. The first one is obvious, this part here. We didn't do that in the previous example. But there is something else, and that is that we're not using x equals 0. Here we're using x equals 1. That makes a difference. It might be obvious in your question, or it might not. But in this case, we need to use the Taylor form where we're using x minus a brackets. The question might have said, use the Taylor method to find a series solution in ascending powers of x minus 1 of this. Obviously that would make it much clearer. So what we're doing here is we're using an a value that is not 0, but is 1. So straight away, think to yourself, a equals 1, and we're expanding in powers of x minus 1. So we're using the slightly different form of Taylor's series that we looked at in the previous video. Everything else stays the same. We've got all of the information that we know. We know x equals 1, and at that point we know that y equals 1. So what I called y0 in the previous example is now a y at x equals 1 rather than x equals 0. And that we know is equal to 1. So that's the first constant here, f of a, the function evaluated at 1. We don't have the first derivative because that's part of our equation here. So I need to put y equals 1 and x equals 1 into this equation to find the first derivative evaluated at that same point, x equals 1. And that is a 1 plus a 1 squared is a 2. So this one here is a 2, and that will go with the bracket x minus 1. Now we need to differentiate our equation to get the second order derivative. So we've got d2y by dx squared, x differentiates to give a 1, y squared differentiates to give 2y dy by dx, remembering your chain rule. Now I can evaluate the second derivative. At that same point x equals 1, and when we're at x equals 1, we know that y equals 1, and we know that dy by dx equals 2. So again, we're putting in all the values we already know from the previous work in the question. So that's a 1 plus 2 times y, which is 1, times the first derivative, which is a 2. So that gives us a 5. Now we don't have a finish point in this question. That's my oversight because I made this question up and didn't put it in. But let's go up to the bracket to power 3. So we'll do one more. Let's differentiate this again. We get the third derivative here. The 1 differentiates to a 0. Then we need the product rule on 2y dy by dx. So if we leave dy by dx alone and differentiate 2y, we get 2 times dy by dx times by the dy by dx that we left alone. And then we need to leave the y alone and differentiate dy by dx, which gives us the second order derivative there. And again, we know all of the information here. We know what this is. We know what this is when x equals 1 from the previous work. So the third derivative evaluated at x equals 1 is equal to 2 times dy by dx, which was a 2, times another one, plus 2 times y, which is a 1, times the second order derivative, which was 5. So that gives us 8 plus 10, which is 18. So we've got our second order derivative, that was a 5, that's here, 5 over 2 factorial, and then we've got 18 over 3 factorial for the next term. So if I put my final solution at the bottom in yellow, we have y is equal to 1 plus 2 times x minus 1 plus 5 over 2 factorial, which is a 2, x minus 1 squared, plus 18 over 3 factorial. 3 factorial is 6. 18 divided by 6 is a 3. X minus 1 cubed. And we will stop there. So I hope you can see that the general method is exactly the same. We're using the boundary conditions given to work out something new, then differentiate it and use all the information that we've got to work out the value of that, differentiate again, use all the information we've got to work out the value of that, and you just keep going. The difference here is that we were not using x equals 0, we were using x equals 1, which means we had to expand about that point, which means we're using this form of Taylor's series expanding in powers of x minus 1. And like I said, sometimes they'll make that really clear in the question, but sometimes it won't be so clear. You'll have to infer it from this statement here. The second thing that was different, use your solution to find an approximate value for y when x equals 1.1, giving your answer to 3 decimal places. This is an easy, maybe 2-mark question on the end of a question like this. All we need to do is put x equals 1.1 into this expression and evaluate it. So I'll do that in white in the middle of the screen so that I can keep everything else there as well. Y is equal to 1 plus 2 times 1.1 minus 1 is 0.1 plus 5 over 2 times 0.1 squared plus 3 times 0.1 cubed. Put all of that on your calculator and we get 1.228. And here you can really see that I made up the question myself because there are no more decimal places after that, so I don't need to round it to 3 decimal places. It is 3 decimal places. There is our final solution. These questions are so similar each time you do them that I am only going to leave it at those 2 examples, and I think that will already be enough for you to have a go at the questions in exercise 7e, and then the chapter review questions for all of the work we've done on Maclaurin and Taylor series, and maybe I'll see you for the final chapter in FP2, polar coordinates.